Check 1, 2, 3. Online students, can you all hear? Check 1, 2, 3. Good evening, everybody. Online students, can you all hear? Okay, final check. Loud and clear, everybody. Okay, everybody. I'm sure it's loud and clear. Right. Okay. So today is week 4, day 3. Week 4, day 3. And we'll be doing 20 MCQs, one structured, one essay. 20 MCQs, one structured, one essay. I'm sure you have done the paper. Now let's discuss. Okay. Right. Right. Read the question. First MCQ. First MCQ. A solid metal sphere of radius A carrying a charge plus Q. Plus Q means all the charges will be there on the outer surface. All the charges will be there on the outer surface. Is placed concentrically inside the isolated spherical metal shell of radius B as shown. So this is your shell. The electric potential of the solid sphere is, look at the board now. If there is plus Q here, there will be induced charges taking place. So here you have minus Q, here you have plus Q. These are the induced charges. Induced charges. Right. Now, how do you find the electric potential? Let's say this point is O. How do you find the electric potential at point O? Right. First, we find the electric potential due to the sphere. So what do? Take all the charges, keep it at the center like a point charge 5. Like a point charge 5. So Q divided by 4 pi epsilon naught A plus. Where is point O if you consider the inner shell? Point O is inside. So potential means potential inside and on the surface both are same. So take all the charges, keep it at the center, find the potential at the surface. Why? Potential inside and on the surface both are what? Same. So minus Q divided by 4 pi epsilon naught B. You have learned this in theory. What about plus Q? What about plus Q? Now plus Q is also what? On the outer shell. Plus Q is also on the outer shell. If it's on the outer shell, if it's on the outer shell, again we need to find the potential at O. Again we need to find the potential at O. So what do? Take all the charges, keep it at the center. Like a point charge, find the potential at the surface. Why? Potential at the surface and inside all are what? Same. So here, Q divided by 4 pi epsilon naught B. From this, these two will cancel off. Your answer is Q divided by 4 pi epsilon naught A. Answer number 1. Answer number 1. Right there. We need to mark the induced charges on the inner and the outer surface. We need to mark the induced charges on the inner and the outer surface. We need to mark the induced charges on the inner and the outer surface. And then find the potential at point O due to all the charges. The potential at point O due to all the charges. The potential at point O due to all the charges. Okay. Now, for the ones who don't know this, remember the potential inside is going to be constant. Up to the radius constant. Outside the radius 1 over r. The potential inside and on the surface both are what? Same. So where is point O? On the surface of the shell. On the surface of the shell means we can directly find on the surface of the sphere. In terms of minus Q, where is O? Inside. Inside the surface. Inside the surface potential and on the surface potential both are what? Same. If I take plus Q, where is the potential? Potential is where? We are finding inside. So inside potential and on the surface potential both are what? Same. Okay, no? Right. Okay. Next one. Mass of Mars is 0.1 times mass of Earth. Mass of Mars is 0.1 times mass of Earth. Distance between Sun and Mars. Distance between Sun and Mars is 1.5 times distance between Sun and Earth. Gravitational attraction between the Sun and the Mars. Gravitational force between Sun and Mars. Capital G. Mass of Sun, mass of Mars. Distance between Sun and Mars, whole thing squared. Divided by. Gravitational force between Sun and Earth. Gravitational force between Sun and Earth. Sun and Earth. G. Mass of Sun, mass of Earth. Distance between Sun and Earth, whole thing squared. Simplify this. G, MS cancel off. Distance between the Sun and the Earth. Distance between Sun and Mars, whole thing squared. Mass of Mars divided by mass of Earth. So here if I take, the ratio will be 1.5. 1.5 whole thing squared. Mass of Mars to mass to Earth. Mass of Mars to mass to Earth. Sorry. Sun to Earth. No? Here Sun to Earth. So this will be reciprocal. Reciprocal. 1 over 1.5 whole thing squared. 1 over 1.5 whole thing squared. Okay. Here 0.1. Check and see this ratio. 0.1 divided by 1.5 squared. Correct answer is answer number 2. Correct answer is answer number 2. Okay. Right. A 6-legged insect stands on the surface of water. So 6-legged insect, one side 3, other side 3. Stands on water. Stands on water. The radius of each flat feet is 2 10 to the power minus 4 meter. Maximum weight of the insect that can be supported by water surface. Surface tension is force per length. That's surface tension. Force is surface tension into length. Surface tension into length. What is the length that we consider? The length is the circumference. 2 pi r. How many circumferences are there now? 6. Sum of forces in the upward direction balances sum of forces downward. Why are we taking 6? Because there are 6 legs. Why are we taking 6? Because there are 6 legs. Here, weight is acting downward. 6 times T times 2 pi r. 2 pi r. Here, surface tension is given. Surface tension is given 7 10 to the power minus 2. 7 10 to the power minus 2. 2 pi radius. 2 pi radius. What's the radius? 2 10 to the power minus 4. 2 10 to the power minus 4. 2 10 to the power minus 4 is mg. Simplify the relationship carefully. Simplify the relationship carefully. Here 4 pi into 42. 4 pi 42. 6 times 7, 42. 4 pi. Here you have 8, 16, 168 pi. 168 pi 10 to the power minus 6. 168 pi means 22 over 7. Let's divide. 2, 28, you have 4. 24 into 22, 8, 4, 8, 4. 528, 10 to the power minus 6. 2 decimal places, 5.28, 10 to the power minus 4. Correct answer is answer number 2. Correct answer is answer number 2. Answer number 2. Okay, no? So here the basic logic, look at it very carefully. Basic logic is this. 6 times surface tension force of each leg. 6 times surface tension force of each leg balances the weight. Balances the weight. Okay. Right. Quickly write down. Right now. So this animal is balanced by 6 surface tension force. 6 surface tension force. 6 surface tension force. Right. Question number 4. Have a look. Question number 4. A raindrop released from a cloud at height h above the surface. The variation of the speed of the raindrops. The speed will reach terminal velocity. So it's starting from a height h, velocity 0. Gradually velocity will reach terminal velocity. This is your answer. Why? Your graph is velocity with height. Starting location here. V equal naught is at h height. As it goes down, height will reduce, velocity will increase, reaching terminal velocity. Correct answer is answer number 2. Correct answer is answer number 2. Write a small sentence there. Starting velocity is 0 at a height capital H. Starting velocity is 0 at a height H. And as the height reduces, terminal velocity is reached. And as the height reduces, terminal velocity is reached. Okay. Right. Consider a situation where weights W are placed on the vertical rods of radii R, 2R, 3R, 4R respectively, made from the same material, keyword same material, have the same length and not attains proportionality limit. Not means still in the elastic region. So it's in the elastic region. So it's in the elastic region, right? Young's modulus is stress over strain. Young's modulus is stress over strain. Cross multiply. X is equal to FL divided by A Young's modulus. X is equal to same load is applied WL pi R squared Young's modulus. Pi R squared Young's modulus. So here X inversely proportional to R squared. Inversely proportional to R squared. Look at this carefully. What are the radiuses? R, 2R, 3R, 4R. R, 2R, 3R, 4R. Right. So you can see the variation is non-linear. Variation is directly non-linear. Variation is non-linear. Look at this carefully. So your answer is going to be what? Not this, not that. So like electric field strength, E proportional to 1 over R squared curve. E proportional to 1 over R squared curve means like this. So the variation is here. There you go. E proportional to 1 over R squared. So look at the variation here carefully. Young's modulus is stress over strain. Rearrange it. X inversely proportional to R squared. Load, length, pi, y all constant. From this you can build the basic relation. Okay. Right. Two boys of identical masses are standing on two identical trolleys A and B, which are at rest on a frictionless horizontal surface. The boy on trolley A then throws the ball m horizontally with a velocity v respect to the earth, and the boy on trolley B catches it. If the mass of the trolley with the boy is capital M respectively, final velocities of A and B are. Final velocities of A and B are. Right. You look at the picture here. So total initial linear momentum equals total final linear momentum. Initially they are at rest. Finally, what's happening? Ball is traveling forward. This is A and ball. Trolley capital M, VA backward. Bring all vectors in the same direction. Bring all vectors in the same direction minus MVA. VA is equal to simple MV over capital M. Velocity A backward. So velocity A in the forward direction is minus simple MV over capital M, because they're given all the answers in the forward direction. Right. So this is for A. Initially, A with the ball is at rest. Then throws the ball. When you throw the ball, A will travel backward. A will travel backward. Law of conservation of linear momentum. Law of conservation of linear momentum. Now what's happening? Now B is waiting to catch this. B is waiting to catch this. Ball is traveling in air with velocity V. B is waiting to catch this. Then what happens? When B catches it, when B catches the ball, both of them travel together with the velocity. There you go. So if I apply total initial linear momentum equals total final linear momentum, initial linear momentum, this is B and ball. Initial linear momentum, ball is coming MV. Final capital M plus simple M travel together. Same direction. So VB is equal to MV divided by capital M plus simple M. Capital M plus simple M. So if you look at the relationship, I think answer number 3 is correct. Answer number 3 is correct. Okay, no? Velocity of A, velocity of B separately found. Velocity of A, velocity of B separately found. Okay, no? Right. Question number 7. Question number 7. Figure A shows the balanced position of light rod. A light rod. No, wait. Carrying an object X and mass M. So here mg, here xg. Take moments about A. Clockwise moments about A equal anti-clockwise moments about A. Clockwise moments about A is capital Mg over L1, Xg over simple L. Simplify the relationship. I think we should erase this X, otherwise you might wonder it's there. Yeah, very good. Here, GG cancel off. X is equal to capital M L1 over simple L. Now we fully immerse this. Tension is here. If I take moments, tension only is acting. Tension only is acting. So on X, upthrust or relax, weight is going to be Xg. Weight is going to be Xg. Density of water is D. Density of the material is going to be how much? So tension plus upthrust equal Xg. Tension plus volume, submerged volume is mass. X divided by density of object. That's the volume. Into density of liquid into G. Xg. Tension is equal to X minus X over rho naught D, take G out. Tension is equal to Xg 1 minus D over rho naught. Density of object. Now take moments about B. Clockwise moments about B equal anti-clockwise moments about B. Clockwise moments about B, capital mg L2. Next is going to be tension. Next is going to be tension. Tension. Tension times L2. Tension times simple L. Tension times simple L. You can go. mg L2. Tension is xg 1 minus d over rho naught simple L. Calculate it carefully. Calculate carefully. Gg cancel off. M times L2 equals what is x? M times L1 over simple L. 1 minus d over rho naught simple L. Simple L cancel off. M cancel off. L2 over L1 is 1 minus d over rho naught. Density of the object. Density of the object. Right. You need to find the density of the object. That's the requirement. That's the basic requirement. Remember, don't forget here L is there. This L is here. Some of you might think L is down. No, no. Multiplication L. Multiplication L. LL cancel out. Simplify this carefully. Simplify this carefully. I'll do it here. Here you go. D over rho naught equals 1 minus L2 over L1. L1 minus L2 divided by L1 d over rho naught. What is rho naught? D L1 divided by L1 minus L2. D L1 divided by L1 minus L2. D L1 divided by L1 minus L2. Answer number 1. Answer number 1. Answer number 1. The first diagram, apply moments, get the relationship. Then tension plus upthrust balances the weight of x. When I'm taking moments, that's important. Tension is important. Here clockwise moment, here anti-clockwise moment. Now I have found x, I have found tension. Substitute here for x also substitute. For x also substitute. For x also I'm substituting. Simplify and get the relationship. Simplify and get the relationship. Okay, no? Right? Simplify and get the relationship. Right. Next one. 3 masses ABC are hanging from a horizontal crossbar as shown in the figure. Each crossbar has negligible mass. If A has a mass of 6 kg, what's the mass of B and C? So this is 6 kg means what's the mass of B and C? All of you all know ratio theorem. You have learned the ratio theorem. If it's balanced here, this is going to be MC over MB. Total weight acting there is MB plus MC. Total weight acting there is MB plus MC. Then this ratio, MA divided by MB plus MC. Because you all know length ratios equal mass ratio. Reciprocal of mass ratio. MB is equal to 3 times MC. MB is equal to 3 times MC. Right. Take moment x over 3x. X over 3x. Here you have MB plus MC. MB plus MC. Here you have MA. MA is 6 kg. XX cancel off 2. MB plus MC is equal to 2 kg. MB is equal to 3MC plus MC. OMC equal 2 kg. OMC equal 2 kg. MC is equal to 0.5 kg. Therefore, MB is equal to 3 times that, so 1.5 kg. What is the order they are asking? B and C. B first. 1.5 kg first, 0.5 kg next. Correct answer is answer number 2. Correct answer is answer number 2. Right there. If we apply ratio theorem, so this ratio is equal to opposite mass ratio. This ratio is equal to total mass here, MB plus MC, 6 kilograms. This can be found by applying ratio theorem. Right. Okay. Which of the following VT graphs shown below would the average velocity over the entire time period? Average velocity over the entire time period is equal to the average of both the velocities at A and B. Out of all of this is for median. We take A and B. Average velocity is total displacement divided by total time. The average velocity is equal to total displacement is trapezium area. VA plus VB divided by 2 into time T2 minus T1. That divided by total time T1 minus T1. T2, T2 cancel off. That is VA plus VB divided by 2. Right. So average of velocity is equal to average of both the velocities at the end. Correct? Correct answer is answer number 5. Correct answer is answer number 5. Okay. The average of the total velocity. How do you find the average velocity? Total displacement over total time. Once you know total velocity over total time, from here if you do the substitution, this is your displacement divided by time. The average velocity is equal to total displacement divided by total time. So total displacement over total time will give you this particular answer directly, which is the average of both the velocities at the end. So correct answer is what? Answer number 1. Right. 8. Motion of a simple pendulum of length L and periodic T is interrupted by object placed at a length L over 2. So this is also L over 2. The period of resulting pendulum is given by what? Now what do you mean by period? Quarter. So quarter, half with length L, quarter, half with length L over 2. So total periodic time is half a periodic time with length L, half a periodic time with length L over 2. Right. Okay. Now? So now simplify. Half a periodic time is 2 pi divided by 2 L over G. Yeah. 2 pi divided by 2. Length is L divided by 2G. L divided by 2G. Okay. So simplify the relationship. This part is taken as the periodic time. This part is taken as T. Simplify. Okay. So if I take this out, total periodic time is 2 pi square root L over G divided by 2 plus 2 pi divided by 2 root 2 L over G. T dash. Now simplify. This whole part is periodic time T. If the length is L, the periodic time. T divided by 2 plus T divided by 2 root 2. Simplify the relationship. Common denominator 2 root 2. Root 2 plus 1 times T. Root 2 plus 1 times 2 root 2 times T. Correct answer is answer number 3. Right there. When the length is L over 2, when the length is L over 2, there is half a periodic time. There is half a periodic time. There is half a periodic time. And when the length is capital L, there is half a periodic time. When the length is capital L, there is half a periodic time. The addition of both will give us the total periodic time. The addition of both will give us the total periodic time. Okay, no? Addition of both will give us the total periodic time. Okay. Right. Moving on. When an object is placed 10 centimeters from a lens, its image is formed 10 centimeters behind the object. So here, when an object is kept 10 centimeters from a lens, behind the object only image is formed. Right. Focal length and type of the lens. 1 over V minus 1 over U equal 1 over F. Light is traveling this way. Object distance is positive, image distance also positive. Focal length. Common denominator 21 minus 2. From this focal length is minus 20 centimeters. So convex lens 20 centimeters, answer number 5. Answer number 5. That's very easy. Answer number 5. Right. Biot-Savart theorem. Now all of us know if it's half a loop, magnetic field strength is mu naught I divided by 2R times half. If it is quarter loop, mu naught I divided by 2R is the full circle. Quarter means multiply by quarter. So here we have a half, here we have a half. I will take magnetic field strength at A. Look at this. Right hand grip rule. Curve the 4 fingers of the right hand. Thumb is indicating inward. Curve the 4 fingers of the right hand. Thumb is indicating inward. Magnetic field. That will give you direction of the field inward. Now be careful. Is this a full circle or half a circle? Half a circle. Full circle is mu naught I divided by 2 times radius 3R. Full circle. Now half of that, there you go. Field is inwards, put the cross mark. If the field is inwards, cross mark. Right. Now here also right hand rule, field inwards. Mu naught I divided by 2R, that's full circle. Half a circle, there you go, inwards. Simplify this carefully. 4 times 3, 12. 12R. Here 12R means mu I plus 3 times mu I. So that is mu I 4 divided by 12, 3R. Mu naught I divided by 3R. There you go. Mu naught I divided by 3R. Right. So current goes that way, comes this way. Here inwards, here outwards. Inwards, here outwards. Right hand rule. Take your right hand. Clockwise inwards, anti-clockwise outwards. So I can write there. Clockwise inwards, mu naught I divided by 2 times radius times half, inwards. Anti-clockwise outwards, mu naught I divided by 2R, outwards means multiply by half. Bring all vectors in the same direction. You can easily see here, which is bigger, smaller denominator is bigger. Minus mu naught I divided by 12R, outwards. Mu naught I divided by 4R, outwards. Common denominator 12R minus mu naught I plus 3 times mu naught I. That's 2. Mu naught I divided by 6R, outwards. mu naught I divided by 6R outside. Right. What about here? Third one. Clockwise, 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 all inward. These two quarter, these what? Full circle. So magnetic field strength at C. Magnetic field strength at C. Magnetic field strength at C is mu naught I over 2 times 3R half inward. Mu times I divided by 2 times. What's the ratio here? R. R and 2R. 2 times R, quarter, inward. Mu times I divided by 2 times radius 2R times quarter, inward. Simplify the relationship. BC, mu naught I divided by 12R, inward. Mu naught I divided by 8R, inward. Mu naught I divided by 16R, inward. Common denominator, let's say 48. Common denominator, let's say 48. Common denominator 48. Common denominator 48. Four times mu naught I plus 6 times mu naught I plus 3 times mu naught I. 13 mu naught I divided by 48 R inverse. So what is your resultant magnetic field strength? A is mu naught I over 3R. B is mu naught I over 6R. C is mu naught I over 48R. Don't need to calculate. When the denominator gets bigger, the value gets smaller. So what can you say? BA larger than BB larger than BC. You know? BA larger than BB larger than BC. BA larger than BB larger than BC. But let's calculate this ratio a bit. 13 divided by 48. How much? 13 divided by 48 is 13 divided by 48 is 0.27. 0.27. 1 over 6. 1 over 6. 0.17. So which is bigger? BC is bigger. So what's your relationship? BA is larger, BC is larger, BB is larger. Correct answer is answer number 1. Correct answer is answer number 1. So right hand rule, half a circle means mu naught I over 2R times half. Quarter circle means mu naught I over 2R times quarter. If you look at this, half, 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 quarter, quarter. Here inwards, here inwards, here inwards. Here outer one inwards, inner one outwards. Subtract. Inwards, inwards. Both are inwards. Simplifying this, we can get the required answer. Okay, no? Simplifying this, we can get the required answer. This taught under Biot-Savart theorem. Second part of magnetic field. I'm sure you all have done this. Right. Diameter of a current carrying wire decreases as shown in the figure. Diameter of a current carrying wire decreases as shown in the figure. The current flows through the wire from left to right. Current is going from left to right. Current is going from left to right. Right. Current decreases along the wire. Current decreases along the wire. So whatever current comes here should go from there. Current decreases from the wire is highly impossible. Yeah. Current decreases from the wire, highly impossible. A wrong. Potential drop per unit length decreases from the wire. Right. Let's try to do V is equal to IR. Delta V is equal to IR. R is rho L over A. Potential drop per length is delta V over L. I rho A. Current is same, resistivity same, area reduces. Potential drop per length will what? Increase. Potential drop per length increases, correct. B is correct. Magnetic flux density on the surface of the wire due to the current decreases along the wire. Decreases along the wire. So magnetic flux density is inversely proportional to radius, distance r. So when R reduces, sorry, R reduces. Now this is from Biosava. This is from Biosava. So when you go there, the radius will keep on reducing. Radius reduces, magnetic field strength will increase. Decreases is what they said, so wrong. Only correct answer is answer B. Only correct answer is answer B. Only correct answer is answer B. So you can see the conditions have written right there. Even if the cross-sectional area changes, even if the cross-sectional area changes, the current through the wire will not change. The current through the wire will not change. Current through the wire will not change. Okay. Right. Right. Electrical circuit. Nice. Battery in the circuit has no internal resistance. Right. Values of VIR respectively are. Okay, look at the board carefully. 11 amperes coming here. 8 amperes going there means 3 amperes is here. 3 amperes here. All these resistors are parallel. That means their potential differences are same. So if I take the potential difference V, current into resistance, V equal IR, I times R, 40 volts. So here also it will be 40 volts. Here also it will be 40 volts. And if you look at this carefully, here voltage will also be 40 volts. All are 40. Who is supplying this? What's the current here? 40 divided by 20 is going to be 2 amperes. So 2 amperes going this way means 1 ampere is going that way. Voltage is 40, current is 1 ampere, resistance is R. R is equal to 40 ohm. So the EMF is 40 volt, current is 2 ampere, current is 1 ampere, current is 1 ampere. There you go. Resistance is 40. 40, 40, 240. Answer is answer number 5. 54, answer number 5. So easy, no? Parallel resistors, potential difference same. Current is given, current times resistance is voltage. Voltage here, if I take this Kirchhoff law loop, is there any inter resistance? No. So this voltage is supplied by that battery. So 40 here, 40 here, 40 here. Here 40, resistance 20, current I can find. Kirchhoff first law, 11 here, 8, 3 here. 2 here means 1 here. 1 times R is 40, R is 40. Now I know. Voltage is 40, current is 2 ampere. This is 40 ohm. Answer is answer number 5. Right. When you are doing this, in the figure shown, X is a resistor, Y is a torch bulb. Torch bulb means filament bulb. Filament bulb. Remember, in a filament bulb, the more the current goes, temperature increases, resistance will increase. Temperature increases, resistance will increase. Okay. They're telling you Ix is 2 milliampere, Iy is 2 milliampere, voltage across X is 0.3 volt, voltage across Y is 0.3 volt. Ix and Iy. When Ix is 40 milliampere, okay. When Ix is 40 milliampere, the filament of the bulb glows. Then the possible voltmeter readings are, so be careful. So be a bit smart here. This is very basic work. Here delta V is equal to IR. So ideal voltmeter system. 0.3 is equal to this current goes that way. 2 milliamperes resistance we don't know Rx. 0.15 means 150 ohm. 150 ohm. Now when this becomes 40 milliampere, will the resistance change? No. Vx is equal to 40 milliampere. Resistance is 150 ohm. 6000 10 to the power minus 3. 6 volt. Vx is 6 volt. What about Vy? Vy. Here ideally, look at this. Voltage at Y, let's say this current is passing through. So here also same, I think. Everything is same. Here resistance is equal to 150 ohm. Now the resistance will increase. 40 milliampere. 40 milliampere. Let's say resistance is 150. 6 volt here. Resistance technically increases, so voltage will also increase. Voltage is going to be more than 6. Vy must be more than 6 volt. So Vx is 6 volt. More than 6 volt, only one answer is there, 9 volt. Correct answer is answer 3. Correct answer is answer 3. Okay. So what's the main idea behind this? In a filament bulb, when the current increases, temperature increases, resistance increases. I will put 150 and solve, but when the resistance increases, voltage also will increase. So it's not 6 volt, it's more than 6 volt. It's more than 6 volt. Right there. In a resistor, we can assume that the resistance remains the same. We can assume that the resistance remains the same. But in a filament bulb, when the temperature increases, the resistance will increase. The resistance will increase. Therefore, the potential difference across it will also increase. Therefore, the potential difference across it will also increase. Therefore, the most suitable diagram, the most suitable answer is a voltage greater than 6 volt for Vy. A voltage greater than 6 volt for Vy. A voltage greater than voltage 6 volt for Vy. Okay, no? Right. Question number 16. Question number 16. A, B, C, D are 4 cups, same size. 4 cups, same size. A and B have rough black surfaces. Now, black surfaces are good radiation absorbers as well as emitters. C and D are smooth, shiny surfaces, weak absorber of radiation or weak emitter. A and C are filled with hot tea act. 50 degrees Celsius. So here you have 50 degrees Celsius T. Here you have 50 degrees Celsius T. Right. And B are filled at T at 10 degrees Celsius. So 10 degrees Celsius here, 10 degrees Celsius here. Right. What can you say? Remember black body radiation, dark surfaces emit radiation quickly, emit radiation quickly. For tiny surfaces, emit radiations weak emission. So this temperature will be 50. This will cool down quickly. A cools faster than C. Faster than C, right? Here 10 degrees, here 10 degrees. He is absorbing. So whatever emitted is absorbed. B temperature will what? Increase compared to D. So B temperature increases faster than D. Basic O-level question. So correct answer is what? Answer number 1. Correct answer is answer number 1. Okay, no? Right there. Dark surfaces are good radiation absorbers as well as emitters. Black surfaces are good radiation absorbers as well as emitters. You can see the way they've asked it. Black surfaces are good radiation absorbers as well as emitters. While shiny surfaces are weak radiation absorbers or emitters. Are weak radiation absorbers or emitters. Are weak radiation absorbers or emitters. So B will absorb heat more quickly than D. B will absorb heat more quickly than D. And A will emit heat more quickly than C. And A will emit heat more quickly than C. A will emit heat more quickly than C. Okay. No? So A is emitting quickly than C. B is absorbing quickly than D. Okay. No? Right. Question number 70. IV characteristic of silicon diodes are shown in the figure. That means silicon diode will work somewhere around 0.7 volt. You have a current going through. If the voltage is less than that, no. But at 2 volts, we have something called Zener. Zener voltage. Zener voltage. Where the diode will work in the reverse bias condition. Diode will work in the reverse bias condition. Right. The maximum and the minimum currents in the circuit are maximum. So current will pass through this. Current will pass through that. Here reverse bias is there. Think carefully and work. Huh? Here 6 volt, here 2R. Here also 6 volt. 6 volt divided by 2 is 3, no? 3V over R. 3V over R. What's the voltage here? What's the voltage here? Here 6 volt. Huh? Here 6 volt. So I2 current easily found. I2 current is 3V over R. Right. 3V over R. Here 0.7 volt. So here the voltage is 5.3 volt. Why? Here 6 volt means here 6 volt. Forward bias diode is 0.7 remaining across the resistor. Clear? No? Here 0.7 volt silicon. So 6 volt here, 6 volt here. Voltage will divide across this 0.7 means 5.3 across that. So what is I1? 5.3 V divided by R. Or 5.3 divided by R. Just forget about the volt. Forget about the volt. So here you can say I2 is 6 divided by 2R, 3 divided by R. Okay. 3 divided by R. Okay. Now, I1 is a large current. I2 is a slightly smaller current. What about I3? Supply voltage 6 volt, 2 volt can be here. So across this 2 volt means remaining 4 volt there, 4 divided by R, I3. I3 is 4 divided by R. Look at the current. I1 5.3 R, I3 4 R, I2 is 3 over R. Largest current is I1. Smallest current is I2. I1 and I2, answer number 3, 70. Right there. So total voltage here 6 volt. Here reverse bias is working. Reverse bias 2 volt means working. So 2 volt here means 4 volt there. Remaining is here. From there we can find the current. Right there. The breakdown voltage or the Zener voltage. The breakdown voltage or the Zener voltage is 2 volts. Breakdown voltage or Zener voltage is 2 volts. Supply voltage across the branch is 6 volts. Supply voltage across the complete branch is 6 volts. Supply voltage across the complete branch is 6 volts. Therefore, voltage across the resistor is 4. Voltage across the resistor is 4. Voltage across the resistor is 4. Clear? So here 6 volt, here 6 volt, here 0.7, here 5.3. Here 6 volt means here 6 volt. Directly I can find. Here 6 volt means here 6 volt. Reverse bias 2 volt means remaining voltage is 4. Okay, no? Right. A multi-scale voltmeter arrangement gives full-scale deflection at 1 volt, 10 volt, 100 volt. Right. So 3 settings for switch S as shown in the figure. So this is reading 1 volt, this is reading 10 volt, and then 100 volt. Right. Okay. Right. Galvanometer G gives full scale deflection for a current of 1 milliamp. Current of 1 milliamp. And has negligible internal resistance. Negligible internal resistance. Right. Okay. So this is 1 volt, 10 volt, here 100 volt. Here 100 volt. Okay. Right. So if I connect it here, let's say we connect it to A. Connect A. I'll mark in 3 different currents. Current will go from here through this, through that, and out of the terminal. These are open terminals. Current can't go. Open terminal. If I apply V is equal to delta V is equal to I times R. Potential difference there 1 volt. Current is 1 milliamperes, 10 to the power minus 3. Resistance is R1. From that we can say 10 to the power 3 ohm. In other words, 1 kilo ohm. R1 is 1 kilo ohm. Now we connect this to B. I'll change the color. Now we connect this to B. If I connect this to B, 10 volt. Connect to B. Delta V is equal to I times R. Connect to B. Current will go through R1 and R2 and then go out. Current coming here will go through R1, R2 and go out. The potential difference is 10 volt. Current is 1 milliampere. R1 plus R2. Look at this 10 kilo ohm R1 plus R2. R1 is 1 kilo ohm. Therefore, R2 is equal to 9 kilo ohm. R2 is equal to 9 kilo ohm. Right, 9. Then do the next calculation. Next calculation. What's the next one? Here. Now I connect this to C. Put a different color. Different color. C. Is it clear? Maybe this one will be clear. C. So if I connect to C, current will come, go through all the resistors, go out. If this is connected here, current will come here, go out. The potential difference is 100 volt. Current into total resistance. 100 volt, 1 milliampere, full scale deflection. R1 plus R2 plus R3. From this you can say 100 kilo ohm equals R1 plus R2 plus R3. R1 plus R2 is 10 kilo ohm. R3 is equal to 90 kilo ohm. So R1 is 1 kilo ohm, R2 is 9 kilo ohm, R3 is what? 90 kilo ohm. Correct answer is answer number 4. Correct answer is answer number 4. Right there, small sentence. If I connect the terminal to A, if we connect the terminal to A, current through the galvanometer will pass through resistor R1. Current through the galvanometer will pass through resistor R1 and terminal A. And terminal A. Terminal B and C are open terminal. Terminal B and C are open terminal. Terminal B and C are open terminal. Right. When it's connected to terminal B, right? When it's connected to terminal B, current will pass through R1 and R2. Current will pass through R1 and R2. R1, R2 and terminal B. And terminal B. And terminal B. When it's connected to part C, point C, when it's connected to point C, terminal C, current will go through R1, R2, R3. Current will go through R1, R2, R3. So current is going through R1, R2, R3. And terminal C. And terminal C. Okay, now? Right. Question number 90. An object carrying a positive charge slides along the incline of surface. Now you can see all the MCQs I solved in the small space given. So remember, the majority idea should be there in your head. And when it comes to MCQ, directly you apply to the point. Don't go and apply equation. I never rewrote equations and all. No. For explanation, yes, I wrote. But when you're doing it, directly apply. Directly apply. Yeah. A point carrying a positive charge slides down an inclined plane. Slides down an inclined plane. A uniform magnetic field is acting as shown in the figure. Uniform magnetic field is acting as shown in the figure. Remember, the magnetic field direction is important. Actually, this is into the paper. Into the paper. Variation of the velocity v of the object, right? Fleming's right hand rule. Field, positive charge going means current. Field, current, force. So there is a force acting or motion. There's a motion acting in that direction. Field, current, motion, force. So if you look at this carefully, mg, normal reaction. Here you have friction force. When the upward force increases, reaction reduces. F increases, reaction reduces. Friction also will reduce. Friction also will reduce. Understood? Friction also will reduce. When friction reduces, what can you say? Resultant force will increase. Resultant force will increase means, look at the board carefully. So down the plane, mg sin theta. Mg sin theta. Yeah. Positive charge moving down the plane. Positive charge moving down the plane. So when positive charge is moving down the plane, Positive charge is moving down the plane. Let me go back. They are telling a positive charge, no, sliding down inclined plane. So moving charge. Moving charge means right. Here induced EMF can't occur. So it's not a closed loop or a circuit. Induced EMF. Here it's a charge. No? So charge moving in a magnetic field. Here normal reaction is there. Fleming's left hand rule. Field, positive charge, current force. Magnetic force will increase. Coming down, velocity increases, magnetic force increases. Magnetic force increases, normal reaction increases. Normal reaction increases, friction will increase. When friction increases, acceleration down the plane will reduce. Acceleration down the plane reducing, that is given correctly by answer number 3. By answer number 3. So here, it's like a positively charged object. So we apply Fleming's left hand rule. Fleming's left hand rule. There. Fleming's left hand rule is applied. Field current force. Field current force. Here magnetic force increases, normal reaction increases. Normal reaction increases, friction force increases. Friction force increases, acceleration will what? Reduce. Okay. Finally, here, look at the question carefully. Here magnetic field is inwards, here magnetic field is outward. Here, as it travels, complete loop inside. Complete loop inside. I'll show this in calculation. Right. Here you go. Here, inwards, outward. Complete loop outside. Slowly loop enter. Complete loop inside. Complete loop inside. Part of loop goes outside. Complete loop there. Complete loop here. Complete loop coming out. Look at this carefully. Right now? Okay. Now, little by little, here everything is full of magnetic flux. Full of magnetic flux. Here, little by little, crosses are reducing, dots are increasing. Here, everywhere dots. Here, everywhere dots. Here, dots are reducing, going up. Fleming's right hand rule, or you use the right hand rule. Little by little, the number of field lines entering increases. Little by little, number of field lines entering increases. According to Fleming's law of electromagnetic induction, it must oppose the change. Field lines are increasing inwards, we must oppose it to keep the thumb outward. Thumb outward. Field lines are going inwards, we must cancel it. So field lines should come outward. So we are trying to cancel the field line. Cancelling the field lines means current will go like this. Current will go like that. Now the number of field lines here and the number of field lines there are same. No change in flux means here induced current is 0. Induced EMF is also how much? 0. Induced current is 0. Induced EMF is also 0. Now look at the board. Here. Number of crosses reducing. Here cross. Field lines are large. Here field lines are reducing. So to oppose it, we must increase it. Increasing means put your thumb inside. Thumb inside means clockwise current here. Number of field lines coming out now is increasing. To oppose it, we must stop this coming out. How to stop it from coming out? Put it inward. So here also there is a induced EMF. Here also there is a induced EMF. Here number of field lines same. Number of field lines coming out reducing, we must oppose it. So current goes in the opposite direction. So this current and that current same direction. Here no current. Here also no current, no EMF. Here current is clockwise. So if you take how the induced EMF varies with time. Induced EMF varies with time. Look carefully. As long as it's outside. As long as it's outside, no EMF. Little by little enters. Number of crosses increase. Reduce. Anti-clockwise current. Again, current is 0. Now clockwise. Here EMF, EMF. Larger EMF there. Here also there's EMF induced. Here also EMF induced. EMF will add. Again, current is 0. Again, anti-clockwise current. Same. This variation should be there. This variation is there only in answer number 1. Only in answer number 1. So you can say number of field lines are increasing. We can assume number of field lines are increasing. Number of field lines are increasing to opposite anti-clockwise until everything comes out. So why it's going up and coming down? When it comes inside 0, no? So it should go up and come down. Yes. Once the whole loop comes inside, EMF 0. No change in flux. So here little by little it will increase. Again it's going to be 0, no? 0 means it will increase and reduce. Here, this side also is creating a EMF, that side EMF. Both EMFs are in the same direction. Current is in the same direction, so they will add. Here also field lines are reducing. Going away means field lines are reducing. I have to oppose it. Field lines are reducing. I have to oppose it. Send more. So current is clockwise. Here field lines coming out is increasing. I have to oppose it. Inward. Here also there's EMF. Here also there's EMF. Both EMFs add, so you have a larger EMF. Here also EMF 0. That's why it large increases, reduces. Here goes out. Number of dot lines are reducing. Increase the number of dot lines. Current is in the anti-clockwise. Here also anti-clockwise. Here also anti-clockwise. Same EMF. Okay. Right there. As the circular loop enters. As the circular loop enters. The number of field lines going through it will increase. Number of field lines going through it will increase. To oppose this change, we can use Maxwell's corkscrew rule. We can use Maxwell's corkscrew rule. We can use Maxwell's corkscrew rule. To oppose the field lines from going inward, we can place the right thumb outward. we can place the right thumb outward. We can place the right thumb outward. So the four fingers indicate anti-clockwise current. So the four fingers indicate anti-clockwise current. Four fingers indicate anti-clockwise current. Next point. When the complete loop is inside, when the complete loop is inside, when the complete loop is inside, no change in magnetic flux, so EMF will be 0. When the complete loop is inside, no change in magnetic flux, induced EMF is 0. No change in magnetic flux, induced EMF is 0. Induced EMF is 0. Now, when the loop enters the next loop, when the loop enters the next region, when the loop enters the next region, what will happen? Number of crosses will reduce, number of dots will increase. So according to Faraday's law of electromagnetic induction, the EMF or the current should oppose this. So number of crosses reducing means you must increase it. So here clockwise. Number of dots are increasing means you must cancel it. How to cancel the number of field lines coming out? Field lines are coming out, to cancel it, you must send in the opposite direction. So again clockwise. Here also clockwise, here also clockwise. EMF will add right there. Number of crosses will reduce. Number of crosses will reduce. Number of crosses will reduce. So we must oppose this. We must oppose this. To oppose this, we place the thumb inwards. To oppose this, we place the thumb inwards, and there will be a clockwise current. To oppose this, we place the thumb inwards, there will be a clockwise current. There will be a clockwise current. There will be a clockwise current. Next line. Number of dots will start to increase. Number of dots will start to increase. Number of dots will start to increase. To oppose this, we place the thumb inside. To oppose this, we place the thumb inside. To oppose this, we place the thumb inside. So again, there is a clockwise EMF. Again, there is a clockwise EMF. Again, there is a clockwise EMF. Both are clockwise, so it will be larger. Both are clockwise, so it will add and be larger. Both are clockwise, it will add and be larger. Both are clockwise, it will be add and be larger. Okay. Next one. When the loop is completely inside the dots. When the loop is completely inside the dots. Flux is constant, EMF and current is 0. Flux is constant, EMF and current is 0. EMF and current is 0. EMF and current is 0. And when the circular loop moves out, when the circular loop moves out, when the circular loop moves out, number of dots will reduce. Number of dots will reduce. Number of dots will reduce. To oppose this, number of dots moving out will reduce. To oppose this, we place the thumb outwards, increasing the number of dots. Number of dots will reduce. Dots means field lines coming out. Number of dots will reduce. To oppose this, we increase the field lines coming out. We increase the field lines coming out. So there will be anti-clockwise current. So there will be anti-clockwise current. Just like the initial case. Just like the initial case. Okay. No? So comprehensive explanation is given. So when induced EMF comes, normally it's a right hand rule or Maxwell's corkscrew rule. EC Maxwell's corkscrew. A lot of things can be done. Okay. Right. So what's your answer? What's your answer? Looking at this, of course, your answer is answer number 1. Answer number 1. Okay. Answer number 1. Right. Okay. Structured essay. Structured essay. To study the resonance phenomenon in sound, you are asked to use glass tube with piston P, set of tuning forks A, B, C, D, found in your laboratory. The piston can move smoothly inside. So moving the piston, vibration length can be changed. Vibration length can be changed. Right. So remember now, be attentive when you are doing the discussion. Now, just like you all, I'm also now from early morning, be the same, each came exactly on time I came, so I'm doing it. So you all are, maybe you all are at home. So therefore, be attentive when the discussion is done. Sometimes maybe in your theory classes, they might have not done these sections, but still be attentive. Take the note down. So when you are learning it again, you will remember this. Is it clear? These for the first shy one. Second shy ones, of course, know all of this. So they are equipped with their earlier knowledge. So it's a matter of reminding old work. Is it clear? Reminding old work. Anyway, carefully look. All the tuning forks are made from the same material. Prongs have the same area, cross-sectional area, 256, 384, 412. There you go. So what's your basic rule? Basic rule means shorter means high frequency. This is 512. Longer means low frequency, 256. Then gradually length reduces, frequency will increase. Here 320, here 384, so here 420, right? Okay. What is the frequency of tuning fork B? Very simple, 420 hertz. 420 hertz, right? That is small sentence there. Longer the prong length, smaller the frequency. Longer the prong length, smaller the frequency. And shorter the prong length, greater the frequency. Shorter the prong length, greater the frequency. Right. For a given tuning fork, briefly describe how you would obtain the reference length. How you would obtain the resonance of fundamental notes. What do you do? First one is start from a very small vibrating length. Vibrate the tuning fork. So if I draw it here, start from a very small vibrating length. Vibrate the tuning fork and gradually move the piston to the right. Gradually move the piston to the right. At a particular instant, the first loud sound is heard. At a particular instant, the first loud sound is heard. First loud sound means fundamental frequency. Fundamental frequency, right there. Start from a very small vibrating length as shown in the figure. Start from a very small vibrating length as shown in the figure. Start from a very small vibrating length as shown in the figure. Vibrate the tuning fork and place it near the open end of the tube. Vibrate the tuning fork and place it at the open end of the tube. And place it at the open end of the tube. Place it at the open end of the tube. And gradually move the piston to the right. Gradually move the piston to the right. Gradually move the piston to the right. At a particular instant, the first loud sound is heard. The first loud sound is heard. First loud sound is heard. First loud sound is heard. Measure the vibrating length. Measure the vibrating length. Measure the vibrating length. Instead of the ear, the sound measuring instrument is kept close to the open end. By varying L naught, we can obtain. Now, remember L naught is the fundamental. Fundamental means greatest intensity. Greatest intensity. Then 2L naught we don't have. Closed tube, no? 3L naught. Third harmony. Then 5L naught. 5L naught means intensity is even smaller. Intensity is even smaller. Okay. Intensity is even smaller. There you go. Right there. There are odd harmonic numbers which occur. There are odd harmonic numbers which occur. There are odd harmonic numbers which occur. And the greatest frequency occurs. The greatest frequency occurs. The greatest intensity of sound occurs at the fundamental mode of vibration or the first harmony. At the fundamental mode of vibration or the first harmony. Fundamental mode of vibration or the first harmony. Okay, no? Right. What is the corresponding resonance length for the first overtone in terms of the in terms of L naught? So if you take 3L naught, very simple. 3L naught, first overtone. Sketch also on the same diagram the expected variation of S with L corresponding to the first overtone. That already I have done. Right. Suppose now you wish to find the velocity of sound in air using all the tuning forks in the above set. In order to use the graphical method to find the velocity of sound in air, which tuning fork from the above set is most desirable to use first? Which one are you going to use first? Normally what happens is we will use the tuning fork having the highest frequency. Why highest frequency? Highest frequency means smallest vibrating length. Smallest vibrating resonant length. Resonant length. Smallest vibrating resonant length. Okay, no? Smallest vibrating resonant length. Right. There is another important physical quantity that you should record during the experiment. What is it? Of course, temperature. Right? When the temperature changes, velocity of sound in air will change. Temperature. When the temperature changes, velocity of sound in air will change. Or temperature in the room. Or just write room temperature. That's easier. No? That's easier, no? Room temperature. In B Roman 2, it was observed that the value of S for 1 instant was 60 decibels. Find the corresponding intensity given as this, right? Beta equals 10 log I over IO. 60 decibel, 10 log. I over IO, 10 to the power minus 12. 0, 0 cancel off. 6 equal log I 10 to the power minus 12. Here 10 to the power 6. I 10 to the power minus 12. Cross multiply. I is 10 to the power minus 6. Watt per meter square. 10 to the power minus 6 watt per meter square. That is your intensity. That is your intensity. Now you can see because of the experience of doing MCQs, these are actually very easy now. Essay question. Essay question. Right. Gravitational fields question. Gravitational fields question. Look at it carefully. What is the speed of the space lab? Radius of the Earth 6,400. Gravitational acceleration on the Earth's surface is 10. So here space lab is here. Mass of the space lab is there. There you go. Radius of the Earth is R. Height is H. Height is H. Somebody is providing centripetal force. Who is providing centripetal force? Gravity is providing centripetal force. Here, mass of Earth, me. Look at the board carefully. They want us to find the orbit velocity. Orbit velocity. Orbit velocity is V naught. Orbit velocity is V naught. Carefully look. Apply centripetal force equal mass into centripetal acceleration towards the center. Who is providing centripetal force? Gravitational force. Mass of Earth, mass of space lab divided by R plus H whole thing squared. Mass of space lab, V naught squared divided by R plus H, orbit radius. From this mass of space lab, R plus H, 1 R plus H cancel off. V naught is equal to capital G ME, mass of Earth divided by R plus H square root. Remember, if you write like this, you will not get any marks. Why? You have not defined the term. What is ME? At least once in the problem, you must define. Mass of Earth. Here, SL, mass of space lab. Mass of space lab. Here, H, height of orbit. Height of orbit. R, radius of Earth. Radius of Earth. V naught, orbit velocity. Orbit velocity. Orbit velocity, right. Orbit velocity. But is capital GME given? No. So you must use the approximation. Gravitational field strength on the surface is capital GME over R squared plus multiplication. So wherever there is capital GME, you can write G R squared. R plus H whole thing squared. Substitute for G now 10. Radius is 6,400 kilometers. Convert to meters squared divided by radius plus 1,700. How much? 8,100 kilometers. Convert to meter. Whole thing square root. Whole thing square root. If you simplify this, you will get the velocity 7.1 10 to the power 3 meters per second. 7,100 meters per second. I think up to 7 or 7.2 also accepted. 7.1 10 to the power 3 meters per second. Remember, the key thing is drawing the diagram. Make sure you define the term. After defining the terms, you write the equation. These are important for you. Okay. Right. Next one. Calculate the minimum energy that has to be supplied to a space vehicle. Space lab, space vehicle. Two different things. To reach the orbit of space from the Earth. Neglect. Just reach. Keyword here is just reach the orbit. Right. Let me go back to the same diagram. Or maybe I should draw it again. I'll draw it again here. Right. Earth is here. Earth is here. Space vehicle is here. Minimum velocity means you are projecting it. Minimum energy just to reach there. Just to reach the orbit. Orbit is H. Radius is R. Mass of Earth ME already defined. Only one more additional thing that you must define here. Mass of the space vehicle. MSV. Mass of space vehicle. Right. What are you asking? Minimum energy. Total energy at A equals total energy at B. I'm writing short form, but you don't write short form. Total energy at A equals total energy at B. Total energy at A is gravitational potential energy minus G ME, mass of space vehicle over radius R, plus half M V squared. Total energy at B is only gravitational. G ME M space vehicle R plus H. What are they asking? Minimum energy. Minimum energy is kinetic. This is your minimum energy. Take this to the other side. GME MSV over R minus GME MSV over R plus H. Common terms, take it out. GME MSV 1 over R minus 1 over R plus H. GME we don't know. We know GR squared, mass of space vehicle. R plus H minus R divided by R times R plus H. From this you can easily say, RR cancel off, 1R here cancel off. So what is the minimum energy? Minimum energy here is, I'll do it here, space vehicle GR, H times R plus H. Okay, substitute. 10 to the power 4, G is 10, radius is 6,400 kilometers, convert to meters, 1,700 kilometers, convert to meters, divided by 8,100 kilometers, convert to meters. Simplify this. Minimum energy can be found. Minimum energy 1.3 10 to the power 11. 1.3 10 to the power 11. 1.3 10 to the power 11 joule. Right. So all this working. So space vehicle just reaches there. Space lab is here. Space lab is going with V naught. So you have to link from here to here. What additional energy is required for the space vehicle to link with the space lab? Now from rest, it has to accelerate. Gravitational here, gravitation there, same. Additional energy. That is the kinetic energy, mass of space vehicle. Increase in kinetic energy, V naught squared minus 0. That's the increase, so additional energy. From rest, it has to accelerate to reach this. Accelerates to reach this. Right. Okay. Now. Simplify this. Mass of space vehicle 10 to the power 4. Orbit velocity 7,100 squared. Simplify the additional energy. This part only is here. Additional energy. How much? 2.5 10 to the power 11. 2.5 10 to the power 11 joule. So just to take here 1.3 10 to the power 11 to connect it with the space lab, 2.5 10 to the power 11. 2.5 10 to the power 11. Right. So reaching here minimum, here to here accelerate. Okay, no? Here to here accelerate. Now how does it accelerate from here to here? Law of conservation of linear momentum. Hot gases are burned, gases are sent behind, rocket is accelerating forward. Remember, rockets travel because of law of conservation of linear momentum. Here, law of conservation of linear momentum. Most of the space movies that you watch, Space Odyssey, all of that, you can see, it starts moving by burning gases. Hot gases are pushed behind. Gas is pushing the rocket in the forward direction. Okay, right. Okay. Finally, after linkage, let me draw this one. Space lab is there. After linkage means here it's linking space vehicle. Now at this orbit, both are joining. Will the velocity change? Will the velocity of orbit change? Go back to look. Velocity of orbit will change. You can see mass of the space lab is cancelled out. Velocity at the end does not have any mass. No mass. Velocity at the end does not have any mass. So even if the space vehicle connects with it, velocity won't change. But that's not what they're asking. After the cargo in the space vehicle, is transferred to the spacecraft, will the speed change? Now here, cargo from here is going in, cargo from here is going there. Will the velocity change? Answer is no. Why? It's an internal process, something happening inside. So the momentum of the object or the system will not change. Right there. Cargo moving is an internal process. Cargo moving is an internal process. This will not affect the velocity of orbit. This will not affect the velocity of orbit because the total momentum of the system does not change. The total momentum of the system does not change. Okay, no? Right. Okay then. So this concludes week number 4 of our work. Week number 4 of our work. Let's see what we have done so far. Let's see what we have done so far. Right. So 4 weeks, 4 papers, 240 MCQ. 240 MCQ. Look at this carefully. How many structured essay? For a week 3. 3 times 4 structured essay. 12 structured essays done. How many essays? 3 essays every week, 4 weeks. Essays. 12 essays done. How much of work? 240 MCQs, 12 structured essays, 12 essays. From each of these, you have what? Learned a lot. Remember, are you progressing? Yes, you are progressing. Are you moving forward? Are you moving forward? Yes. Everybody who is weak, where are you going? Slowly you are moving upward. Where are you going? Slowly you are moving upward. Remember, you are on an upward trend. Make sure you keep the same intensity every day. Remember, you are moving forward. The worst thing is you're not moving. But doing these things, you are moving forward every day. The best case scenario, because there is nothing to lose for you. The best case scenario is you're moving forward. Since you're moving forward, and even though some people are going up like this, some people are going with a small gradient, some people even smaller gradient, whatever happens, you're still moving up. So be proud of yourself and keep on working with the same intensity. Remember, discipline and commitment will guarantee get you your required result. So enough for today. I'll be putting what you call week number 5 papers. Week number 5 papers, most part because most are requested it early tomorrow. So therefore, keep working. Stay home safe. Good night.